We will see some more when we talk about linear regression, some other ways of identifying outliers. Just a couple of things. Discrete distributions can be approximated to continuous normal distribution. We saw that with the binomial demo. The rule is if NP is greater than 5 and NQ is greater than 5, then a binomial distribution can be approximated to a normal distribution. And when you are approximating normal means mean and variance. Mean of a binomial is NP. Variance of a binomial is NPQ. So you don't need to get the mean and variance separately. You just use NP and NPQ and then use the normal distribution method of finding probabilities. Okay. There is something called continuity correction that I will talk about tomorrow. This is binomial approximated to normal. NP and NQ both have to be more than 5. Poisson can be, we saw that Poisson starts looking like normal thing. And rule of thumb, more than 15. Some people say 10, some people say 20. Doesn't matter, approximately there. Okay. So this is what continuity, but again, discrete is turned into a continuous thing, so there is a problem, and that problem is fixed using the continuity correction. We will start with that tomorrow. Okay. So this is what we have covered. So what have we covered today? Property distributions. Did we start with that? What did we start with? Yeah, the revision was quite a bit. Okay, we covered that, and then we started with property distributions. Mass function and random variable, and then property mass function and density function. Mass function was for discrete, density for the continuous. But we saw that they are related to histograms closely. Histogram was the frequency plot. Frequency can be converted into probability by dividing by the total. The frequentist approach, a posteriori method of calculating probabilities. So that's what gave us the y-axis was probability instead of frequency, and that was the probability mass function. For a continuous variable, probability at a fixed point is 0. Getting that exact value not possible, but a small range can be done. The probability density, so probability per unit change in the x-axis value is what the probability density is. So that is what the continuous thing was. And then we saw common probability distributions. Discrete were first one geometry. Bernoulli was here, the experiment, and Bernoulli and many Bernoulli experiments continued to get the first success was the geometry. And the expectation of that, any probability distribution, I need expectation, variance, and the probability of some event in the distribution. Normal, I was trying to understand the area to the left of Julie's side. Some value was there to the left. So that is what I am normally interested in, some value in the distribution. So for geometric, the expectation was 1 over p, and the variance was q over p squared. And then we came to binomial. What was binomial? Number of trials are fixed, and I am counting the number of successes. Probability of that. And that, so PMF for a geometric was q to the power of r minus 1 times p. R minus 1 failures and the R1 is a success. That's one. NCR, p to the power of r, q to the power of n minus r is the binomial one, where I am interested in number of successes, fixed number of trials. And then finally, and the expectation for binomial, NP, and the variance was NPQ. Then Poisson. Average number of events is given. I am interested in some probability of some other number of events happening. PMF was e to the power of minus lambda. Lambda was the average number of events. Lambda to the power of r divided by r factorial. Then we came to exponential distribution, which was same Poisson process, but instead of number of events that are happening, I am interested in time period. The time period before the next event happens. Number of events, now not number of events, next event happening. What is the time gap between that? Since that's continuous thing, it's a continuous thing. And as I am interested in the next event only, the first success, the next success, it's a geometric analog in the continuous distributions. The expectation of that was 1 over lambda and variance was 1 over lambda square. Expectation and variance were Poisson time for the lambda, which is given in the problem itself. Okay. No calculation also in its distributor. And so with those we finally then came to, so 3 important discrete distributions done, then exponential, and finally the most important distributions of all, the normal distribution. Tomorrow we will see the most elegant theorem in all of statistics, which makes even not normal things normal. Okay. So normal distribution is what we saw. There we need to know the mean and the variance. There is a very powerful empirical rule that you must remember from now on. You cannot afford to forget that. It has to be remembered. 68, 95, 99.7, which means 68% of the data is within plus minus 1 standard deviation from the mean, 95 within plus minus 2, and 99.7 within plus minus 3. But whatever it is, I am either interested in finding the x-axis value or the area under the curve. P norm gives me the area under the curve corresponding to the x-axis value I am interested in. Area is always to the left. If I am interested in right, 1 minus of that. Or I know the area under the curve. I am interested in what is the corresponding value of x up to which this much of data is present. So 80% of the data. What is the value in this distribution on the x-axis value to the left of which 80% data is there? So 80th quantile or something. 80% of the data is less than that. That's where the Q norm comes, the quantile. So either P norm or Q norm, you are interested. And that's what it is. Really simple. Any questions? And we also saw skewness and kurtosis, and then standardization. The standardization was x minus mu divided by sigma. Skewness was, so this was what we call z-score or z-score. Skewness is z cubed. Kurtosis is z to the power of 4. Minus 3 for the x, the comparison with normal. The normal distribution, actual kurtosis value is 3. But we want to show it as 0, so minus 3. We just subtract 3 from everything. So that's what we did. And for the shape of a distribution, we said mean, which is the expectation of the data of the distribution. Then squared deviations, expectation of the squared deviations from the mean, which is nothing but the variance. Expectation of the cubed deviations from the mean gives you the skewness. Expectation of the 4th power deviations from the mean gives you the kurtosis, which is the weakness and the tailedness of the data. That's what it is. Okay, good. Thank you very much. Let's have lunch and I'll come back tomorrow and nice, very beautiful things done using normal.